Now, let me show you real quick what the actual Schrodinger equation is, and then I'll tell you why that's wrong. So, like I said, I know this is a little offbeat, but I mean, I could, between this and the next thing, if there's any homework questions or something, or maybe, well, maybe office hours, right? It's just that this is kind of neat. Okay, so here is the Schrodinger equation as you've known it. And let's go back to what hopefully seems like a simpler time. I'm just doing a one-dimensional deal, obviously. Okay, so this is what you've seen. And back when we were doing free wave, hopefully those are like, oh, those were the good old days, right? E to the ikx is an answer. You know that k is the de Broglie, highest the de Broglie wavelength. It's also the momentum, has those two roles. But momentum is all about, de Broglie wavelength is related to the momentum. It all makes sense, right? This is not true. This is not what Schrodinger derived. This is what Schrodinger derived. I h bar d dt. So I have to put in two variables now. I have to make two changes. Schrodinger derived this equation. It has time in it. So if you think about it, if quantum mechanics is like the equation for everything, where the heck is time? It needs to be there. Because, I mean, if things don't change in time, what the hell? There's your time. Question?
There's supposed to be a plus somewhere in the middle there, right?
Yeah, equal. Oh. Right. So instead of E, so kinetic energy is equal to E times the wave, energy times the wave function. It's actually the time derivative of the wave function. Okay, so why was I showing you what I showed you? Because guess what? Now, I know I harped on this, and you probably kind of thought, like, why am I always barking about this? Am I just saying it's a big deal because I feel like it just to talk about something? Separability. It turns out I showed you what I showed you because of separability. So if you do the normal separability thing, what you find is you've got minus h bar squared over 2 times mass. I've got the x wave function, double derivative. Of course, x is caught there. Time got through, but then time was wiped out. Then you've got the same thing over here. I'm bringing these over to the left. So again, the spatial wave function was wiped out, not the time. IH bar, let me get double derivative with respect to time. Okay, so again, there's our math speed. I put this in the separated form, which is again more of the math-friendly form. It also shows separability, right? So separability, x's, t's, separated. Therefore, it is proper to say that there is a sine and cosine type of wave function, and then there's another one for time, which I'm about to show you. Okay, so I know this projector is annoying. I'm going to actually splice it in when I make the video. Okay, now, you know that the way that when these things are separated and equal to a constant, each miniature Schrodinger equation is equal to its subconstant. Just like in the last hour, I showed that all the radial parts are just contribute the rotational energy, L times L plus 1. H bar squared, something, whatever. Okay, now, guess what? What do you think are the constants for this thing? Each term is a constant. There's one minus the other to equal 0. Guess what that constant is? 0 minus 0 equals 0 would work, and that often comes out to be the case, not in this one.
Are they just equivalent to each other?
Well, they are. Yes, and that's part of the clue. And 0 minus 0 does work, by the way, Mathland. That is fine. That's just not the answer in this case. But they have to be equal, right? They have to be equal because they have to subtract each other to 0. So they are equal to the same constant.
Just a question, are you asking us what that contour represents? Or?
Well, but this is just a separated wave function. This is the real Schrodinger equation in time and space. I've separated this time and space wave functions into miniature Schrodinger equations because they're equal to a constant, that constant 0, 0 is still a constant, each sub-Schrodinger equation is equal to its own constant. But can you guess what that constant is? Can you guess what that is?
Have a guess.
Yes.
Give me position.
Okay, you're thinking of, you're hot. You're getting close. Yes, wasn't quite right. Now think about what we've been doing the whole time. What was this?
Oh, the energy?
Energy. The sub-Schrodinger equations are each equal to energy. Right. So you see, if all of this is equal to energy, you get to what we were doing. Right? Remember, separate and solve sub-Schrodinger equations. You have been seeing a sub-Schrodinger equation. You've been seeing the separated form of the real deal. That's what you've been seeing the whole time. But the real deal looks like this. Okay, now, note that you can actually solve this thing. So you've done this. You've done this to death. And you've done this as far as a person actually can do it, by the way. Just a heads up. You can't solve the Schrodinger equation analytically. That means with e to the I phi and cosine and all that. You cannot solve the Schrodinger equation analytically past the hydrogen atom problem. You have actually seen all the problems for which we can sit down on pen and paper and do solutions. When you do things beyond the hydrogen atom, like helium, you need a computer at that point. And that's a numerical solution. Okay, now for the, now this guy we can solve, okay. And what that ends up being is, let me actually look at my notes. So you end up with IH bar, wave function, and I'm still going to put this in the mathematical form, in the separated form. Again, mathematicians actually like that. I like the appeal of whatever works, you do this operation. Whatever works means the wave function. Whatever works, you do all this and you get a constant. I kind of like that. I like this a little bit better than the eigenvalue form, the chemistry form. So this is the math form. Okay, now the solution, the time solution is very simple. E to the minus I energy time over h bar. That's the solution. And you can check it out yourself. It's very easy. And therefore, the real wave function is e to the minus I e t h bar. What the hell wrong? H bar times. Okay. So the real Schrodinger equation is take this stuff that you've been working with the whole time and multiply it by that. Doesn't look too bad, right? It actually ends up being slightly more complicated because the way you actually solve this is you actually do it this way: e to the minus I t over h bar, the operator. Now, you remember when I had you solve what's e to the derivative? Right? You were like, what the hell is that? I was actually trying to show you a little bit of what time evolution looks like in quantum mechanics. E to the Hamiltonian. And just like you take 1 plus x squared, and then you end up doing that with the Hamiltonian. I know this looks easy, but it's actually kind of hideous. So anyway, well, there you go. Like I say, since we have the bit of a funkiness in terms of no one cared after a test, and I didn't really have much else to talk about, I wanted to show you this. But now that I can take a spatial wave function and multiply by this, it is actually slightly harder. I can show you what that actually looks like. Now, the reason that's important is it gives you a natural, for one, it shows you that this is a dynamical theory, because what good is a theory that describes things if those things don't move, right? It's like nonsense. Of course things move. And in many ways, it's more important to know how things move. So in the last night and this morning, I was making videos.
Alright everyone, so this is what time-dependent quantum mechanics looks like. Here we have in red a potential energy surface. There's a very, very large barrier to the left. We can't really simulate an infinite potential on a computer, so we just made a very high potential barrier on the left. There's a 1 nanometer trap from 3 to 4 nanometers. That's where we see our wave function, and a finite 1 eV barrier to the right. Now we made the wave function in blue kind of curvy, and that's so that it would have a lot of kinetic energy because it needs kinetic energy to get over that barrier. All right, now we're going to see the computer animation of the time evolution of the wave function. It's not quite the same level of animation as what you just saw, so there's a little weirdness there. Okay, so here we see the wave function evolving in time. So this is what quantum mechanics does. Quantum mechanics is inherently a time-dependent theory, and so now you're seeing that for the first time. Here we see the wave function indeed does have enough kinetic energy to get over the barrier, and you also may notice the time that it's taking. It's on the order of 10 to the minus 18 seconds. That's an attosecond. So electrons move very, very, very quickly. One of the reasons we need quantum mechanics. Notice that the wave function has become much wider as it moves to the right. That's because it's lost kinetic energy. It's lost kinetic energy because it's in a high potential energy region of the potential surface. Also notice how the action seems to have slowed down quite a bit as the simulation moves forward. Again, it doesn't have much kinetic energy because it's moved to the high potential part of the well. Now, a lot of people have asked me, what does it mean for a little bit of the wave function to have been retained in the original trap? To explain that, let's look at a little bit more of an interesting example. I've recreated the potential surface with a little bit of a difference. I've started out with a lower kinetic energy wave function, just a nice little bell-shaped wave function in blue, and instead of an infinite potential on the left, I've drawn a half harmonic well. So basically, I've taken this electron and I put it up a hill. That is exactly what I've done. And what's going to happen is it's going to slide down the hill, and you're going to see that as we blend here to the actual computer animation. Again, doesn't quite look as nice because I'm not good at computer animation, but regardless, all right, so here we go. The wave function first wants to spread out. That's why we're expanding a little bit so you can see it. The wave functions are normalized. These are the wave function squared, the probability density. And here you can see it's clearly moving to the right very quickly. And it's penetrating the barrier. We put that electron high up enough along the hill to have enough kinetic energy that it could get through the barrier. And now you're seeing what quantum reflection really looks like. A lot more interesting than solving those equations in the class, I bet. It looks like a surfer cresting a wave. And here we see, again on that same attosecond time scale, here we see again the wave function split in two. Now does that mean that this electron has split in two? No, what's happening is, imagine if you could actually build this potential surface and put an electron in it. What it means is, looks like 90% of the wave function has gotten over the barrier. That means 90% of the time you do this experiment, the electron gets out of the trap. About 10% has reflected off and has remained inside the well, and that means 10% of the time you did this experiment, the electron doesn't get out.
Now, I told you that the Schrodinger equation is a big fat lie. Let me tell you how that works. Okay, so what do I want to do here? Okay, so we do h bar squared over 2 times the mass, d r squared. I'm putting this in the first way that you see the three-dimensional, remember this is the three-dimensional kinetic energy operator. So I'm just writing this SOD out. Again, you don't, unfortunately, you know me well enough to know that you don't need to memorize this. I just hope that one reason I throw this at you so often is to make you comfortable with all of it. I can imagine if I threw this at a freshman, a class of freshmen, even though they know what sine functions are, they would look at this and probably throw up on themselves. Okay, here's Coulomb's law. Okay, yeah, so there you go. There's the Hamiltonian for the deal. The wave function is separated for all the weird reasons that I didn't really explain last time. There you go, and yada, yada, yada. Okay, so here's the deal. Remember that the angular part goes as like h bar squared, L times L plus 1. Then you get an energy based on the radial part. let me ask you this. Where's spin? Right? Notice that when you solve this thing, you end up with an m quantum number for the phi. You end up with an L once you solve the rotational part for real. And then you end up with the energy from the radial. So you've got the Schrodinger, the hydrogen states are right. They're like 1s, 2s, those are the radial and quantum numbers. 1s, 2s. Again, the 1 and 2 are the radial quantum numbers. S is SPD, those are the L's. And the M's tell you PX, PY, PZ. All right, so you're all, you knew that as freshmen, right? It's just a little bit more real now that you see where it comes from. Yeah, we're all okay? You get that, right? SPD, S1S, 2S, 3S. All right, I just drew this a second ago. What are the up and down again? What's the up and down?
It spins.
Where's spin coming out of this? So S comes out, P comes out, the different rows of the periodic table comes out, but really one of the most important things to electronic structure, spin does not come out. It's not like a subquantum, it's not a sub-Schrodinger equation.
So would it be the theta?
No, the theta is the M, right? That's PX, PY, PZ. So P and the PX, PY, and PZ are the M's from there. But where's spin? Right? You can't answer me because it doesn't show up. Now again, it doesn't show up, it's just not there.
Right, because you don't know the thing's direction with absolute certainty, right?
No. The answer is that this is all wrong. The answer is this is wrong. Spin, this part, the up, down, now again, look, I'm drawing a 3D, right? Because there's 5 of them. So there's 5. There's only 5 because their L is 2. That's a d orbital. All of this, and so you have to be on like n equals 3, right? The transition metal block, 3, 4, 5. All of this comes from here, but not this up-down bit. And when they realize that, they realize Schrodinger equation's wrong. Even the time-dependent one, even that one is wrong. It's all wrong. Because if you did it right, the S quantum number, spin, should show up as a sub-Schrodinger equation. It has to be a sub-solution that says that there's these up-down things. And there isn't. So all of this is wrong. Okay, so wipe it all out. Now, I'm going to show you what the real equation is. It's called the Dirac equation. But the reason we don't show you this is that the differences in the answers between the Dirac and the Schrodinger, the only time that they're actually kind of big is when when the answers are like way different, is when something's moving the speed of light. And in chemistry, that actually kind of does happen. In gold atoms, the s electrons, the 1s electron, all right, so gold has a heavy nucleus, right? Big positive charge. Think about the 1s electron. It's almost orbiting this giant nucleus. It's spinning really quickly to avoid crashing into the nucleus. The 1s electrons of gold in heavy elements, they're almost going the speed of light. So you actually cannot use the Schrodinger equation to solve the electronic structure of gold and big heavy things like that. Okay, the real thing, the real deal is to note that Einstein said, so what you're doing is you're mixing in relativity with MO is the rest mass, we'll just call it an electron. Right, the rest mass, you know that mass increases as things speed up. So I'm saying M0 is a rest mass. Okay, now let me point out where the Schrodinger equation chokes. It's real simple. All right, P squared is like the del squared, right? Times the wave function. Now, don't worry about time dependent, right? So when we do what we've been doing non-time dependent, it's 5. Notice that we've been saying P squared over 2m. Here, I'll write minus h bar squared over 2m is equal to energy. All right, you see where it chokes? You see the choke between Einstein's relativity in Schrodinger equation? You see where there's a problem? Huh? Where does not compute happen? Right, E squared. Einstein says E squared is equal to momentum squared. Schrodinger said E is equal to momentum squared. Well, that doesn't work, right? E squared is not E. So one of these people is wrong. Now, it's not like a stupid unit thing, like, no, wait, well, that's just flat out wrong. P squared C squared ends up being kilograms squared meters to the fourth per second to the fourth. That's a joule. P squared over 2m is a kilogram meter squared per second squared, which is a joule. So this works. P squared C squared is a joule squared. P squared over 2m is a joule. Units work fine. It's just a fundamental way of setting it up. If you set it up Schrodinger's way, great. You get a lot of answers that are correct until things start moving the speed of light, but you actually do run into that in the periodic table for the reason I just meant. This thing should be the real deal. You just have to mesh it with quantum mechanics. Now, one way to do that is basically do this. Right? So this is how Dirac did it, was to basically take the square root. So what Dirac does is he takes what you've done, he tacks on this term, you gotta add this little part here, and he takes the square root of it and says that equal to energy. Now actually don't mind, none of you write this down at all, I just kind of want to show you because it does get kind of mind-numbing from here. But so the way this works is, so the damnedest thing is though, all of this has been a real nightmare. Now let's take the square root of it. Let's take all these operators, operate on a wave function, and then take the square root of that, and then still have an equal energy times the wave function. Yeah, no, that sucks, right? That's going to be impossible. Okay, so here's what they figured out. Okay, so what you'd like this to be is like P times C plus MOC squared, right? You'd like this to be true. Because then we have our operators kind of like normal. All right, but it's the square root of A squared plus B squared. Here, let me write that down. Okay, so this is like A squared, this is like B squared. Is this true?
No.
No, it's close, but no, that is not true. This is the dilemma they had. They know that they can't, the square root of all these operators, screw that. No, not doing that. They know that they need to whittle, they need to have the operators, not the square root of the operators. But that means that you run into this problem. You run into this problem. Right? There's no way to simplify this. But they have to. So how do you do it? Is it possible? What do you think? It's actually possible. It is for the weirdest, they figured it out in the weirdest way. This is why I think this is so cool. Again, geeking out, but whatever. Okay, it turns out that what you do is you're going to multiply this SOB times, multiply A times alpha, multiply B times beta. Now I need to make this look like A squared plus B squared. So I'm going to multiply it by itself. And I note that this can be made to look like, tell you what, let me leave it like this. Okay, so again, my purpose is to turn this into something that's tractable. Let's just call it this. I need this to turn into that, but it should be impossible. The trick is to do this, and by the way, alpha is equal to 1, beta is equal to 1, right? So you see, that's the trick. You just got to figure out what alpha and beta are that do that. And you notice that there's one other thing. Because of the foil, you notice that there's a little bit of a foil. There's a cross term. There's a cross term. So the reason this works is you assume that alpha is 1, beta is 1, so it doesn't actually do anything. But the cross term that when you FOIL this out will be 0. And if that happens, then you're fine, right? all you gotta do is find functions like Dirac deltas or some jazz that do this. Any idea what does that?
Imaginary?
What's that?
Imaginary?
No, here, let me just write it down. Matrices do it. The answer is a matrix. A 4 by 4 matrix. That's beta. Alpha? Now, alpha is going to end up being with the momentum, and you know momentum is XYZ. This is just, remember, this is like MC squared, right? So that just kind of is like a constant that gets tacked on. I don't know that it really does anything, it just is, it's just there. So you're going to have an alpha X, alpha Y, alpha Z. So let me just point that out. And what this is, it looks like this. You see they're orthogonal. Now hopefully you remember your matrix, this and that. I don't remember my matrix. At one point I had a class on matrix math, linear algebra, right? It's kind of neat, but whatever, I don't really remember it. But I do recall that when all the elements are 1, then the matrix is basically a 1. And the fact that these go at different angles, right? Left, right versus left, right, left versus left, right. That makes this happen. So, what you end up with then is, let me write this down and then we'll just end with that, is the Dirac equation, which, cool, but is unbelievably painful to solve. Let me find, sorry, where am I at? It ends up looking like this. Okay, so we've got our derivative with respect to time. We've got our kinetic energy, there's momentum. Then we've got mc squared, right? Seriously, mc squared, just like, you know, atomic bomb stuff, Albert Einstein stuff, that's the exact same thing. So there we go. So you see more of a time. It looks more like the time-dependent Schrodinger equation, except that I've got a C. So you see what I've got here. So here I'm just trying to put this more like you're used to seeing. Sorry, that's time. Okay, so normally this is energy times the wave function. Actually, I think it might still be. Okay, but instead of, so this is E side. So instead of del squared, kinetic energy operated squared over 2m, you've just got momentum. Momentum times wave function. Instead of momentum squared over mass. Right, you follow me again? Instead of momentum squared over mass, like you've been saying a gazillion times in our SIGO, it's now just momentum. It works because it's multiplied by c. That makes the units work. And then this is, seriously, mc squared. E equals mc squared. That's this part right here. And then you got these matrices. Okay, now what that means is every wave function are 4 different wave functions. Right? 4 in the way side look the same, so be careful. Because you have 4 matrices, a matrix, a 4 by 4 matrix, which you had to do to make this work, every time you solve a problem, you have 4 independent answers. Now, guess what that means? That means that, for one, spin actually does come out of the thing. That's one thing that'll happen, and I can't really, that ends up being kind of complicated, so let's not worry about it. But if you're solving an electron, when you're taking like the square root, so it's like you're taking the square root, you end up with something with a positive charge and something with a negative charge. Right? So you see what's happened? It just predicted antiparticles. So the reason you have 4 different ones is that you get antiparticles. You get positrons and electrons, which are true. Right? Antimatter. It predicts antimatter. And so what ends up happening is not only is one of your wave functions, like the one we're solving now, you get 3 others. Those are antiparticles, antimatters. And the way they behave, like whatever the electron does, the positron does the exact opposite. Some people think that antimatter is actually matter going backward in time, because you could not tell the difference, by the way. And I think that's, I don't believe that, but I mean, I don't know, but that's cool. It does mathematically work out that way, so I thought that was kind of neat. Anyway, well, that's all I have. I just wanted you to know that this stuff exists. It's kind of cool. I hope you like it. But of course, it's not on the test or anything.